So also when you try to encode real life problems coming from industry in Dimex, this can result very huge Dimex files. I'm talking about gigabytes. In the subsequent slides, it is written how you can start with a SAT solver, how to verify any system. I mean, for example, a software system or hardware system or a logic puzzle. It's written here, you will read it. I hope you will understand it. The most important slide here and the most important concept is called bounded model checking. It's explained in the lecture notes. Please read it, and if you have any question afterwards, you can ask me in the Discord chat. Anyway, we can use this approach if we want to encode a large real-life system into SAT, and the result is typically a very huge formula with several copies of the original formula which describe the system itself. So you can imagine that this formula can get really huge. Okay, so this is inconvenient. Rather, now we are going to learn a new approach, which is called SMT. And the rest I already explained. So, what is SMT? SMT is actually set solving, I mean satisfiability checking over certain theories. So you want to check if a formula like this is satisfiable, but this formula looks a little bit strange because, okay, at some point it's all right because you use the well-known logic operators, but, and this is interesting, those connectives connect how to say relations, for example, over, for example, numbers. So this is what I highlight here is not a logical expression. It's a expression in mathematics with a variable of type integer with a number 3 with this relation greater than. So this is not coming from logic. This is coming from some mathematical theory in the background. So we combine set solving with such theories. This is what SMT is. Okay, the theories can be of different types, kinds. We can use integers, the theory of integers in the background, or if you need real numbers, then you can use the theory of real numbers, or if you want, you can use arrays. So there are several theories you can pick in SMT. So in the lecture notes and also today, I will only pick the theory of integers. This is the easiest one, and this will be completely sufficient for us. Okay. Okay. So I picked a theory, and now I would like to describe certain problems like this one here, this logic puzzle for SMT in order to solve this problem, to make the computer to solve it. This is the point. For this, I really need to know the standard format for SMT solvers. This is called the SMT-LIB format, which is more human-oriented than Dimex. So it's easier to read because it has textual instructions. like in a programming language. I show you the instructions, the most important instructions. So the instructions have names. Okay, this is not a very huge novelty, but compared to Dimex, it is a very convenient solution that I have instructions, not only numbers. In Dimex, you have only numbers. And you can use also types. Like in programming languages, you have a type integer, a type bool, real numbers, and so on. You can use concrete numbers in the source code of SMT-LIB. You can use operators like addition, multiplication, relational operators like greater than or equal, and so on. So this format looks much more this format much more likes like much more looks like a programming language. Okay, so now let me talk about the most important instructions in SMT-LIB. Most importantly, this guy here and that guy. So these two are the most important instructions we will use all the time. Similar to a programming language, you definitely need to declare variables. You know what it means? So what does it mean? What does it mean to declare a variable in C#, for example? Please help me.
First, we declare the type for example, integer, then the name.
Yes.
Then we can end it, or we can just declare a value for it.
Exactly.
Which can be changed through the program if we didn't type const at the beginning before the type.
Yes, exactly. So this is completely true for programming languages. First of all, you are right. You have to declare the type of the variable and the name of the variable. This is what we call variable declaration. And optionally, you can assign an initial value. So in SMT-LIB format, you should also declare the type and the name for a variable. This is what you can use this instruction for. It's called declare const, and it has a funny name because it says constant inside. It doesn't say it's a variable, because in SMT-LIB format, in SMT, you can assign a value to a variable only once. You can never change this value again. You have to use to this. It's different than programming. It's rather this gives the description of a logic problem. This is why we can assign a value to a variable only once. As you just told us, in programming, you can change the value of a variable arbitrarily many times, but this does not hold for SMT. Anyway, thank you. Then the other important instruction is how to pronounce it, assert. Actually, in programming languages, you can also find this instruction. I'm pretty sure Java has it, and I think C# has it as well. Currently, I'm most of the time I write programs in Python, and Python also has this assert instruction. Anyway, in programming, you use this for checking a condition. If this condition holds, then the execution of the program continues. But if the condition does not hold, then your program stops with an error message. So basically, the assert instruction in programming languages, and also here, checks if a condition is true, and if it is not true, then it's end of story. We exit from the program. So we will use the assert instruction to put conditions or logic statements in the code, basically, and this is what we need all the time. Okay, in a minute I will start to write a SMT-LIB a problem, and I will show you how to execute it. But first, we need to talk about this guy here, the checksat instruction. So after you declared all the variables you need and asserted all the statements you need, you want to know if they are satisfiable, right? This is what you want to know at the end. And this is the instruction which checks this for you. Okay, guys. Oh, okay. Yeah, I will talk about those two additional instructions later on. But let me switch to the next slide, because, of course, as in other programming languages, you can also use operators like, for example, addition, division. You can use, you can check the equality of two variables, for example. Here you can use this simple equality sign, not the double one. Distinct stands for non-equality. You can use logic operators and so on. The rest are not, you can understand the rest if you read about them in the lecture notes. Okay, so let me solve a problem now. What kind of problems I could choose for the demo? I could check logical formulas. I could check any of the logical formulas we used in this semester. It would be so easy to encode in SMT-LIB and then call this instruction checksat, and the SMT solver would check if the formula is satisfiable or not. But now I will choose the second type of problems. I will check equations or inequalities in mathematics, and we will see what will happen. Okay, so first of all, I need an SMT solver to use. There are several SMT solvers on the market. I already explained this. I'm going to use Z3, and which has an online interface as well. So this is what I'm going to use now. Okay, so here it is. Okay, so this starts with an example. This is already in SMT-LIB, in the SMT-LIB format. Now let me delete it and let me start to encode a new problem into SMT-LIB. I was looking for a system of inequalities which has no solution. So I found this on YouTube. It's amazing. Certain people, what problems choose to make a video out of it. Anyway, and this is what I'm going to encode in SMT-LIB. So if you look at it, it has two variables, right? X and Y. So we definitely need to declare them. So how to declare a variable? Do you remember what is the instruction for declaring a variable?
Const.
What?
It's something with const.
Yeah, declare.
Yeah,
it's
const.
easy. Declare const. Yeah, declare const. Okay, great. Immediately you can look something strange. So I will put every instruction between parentheses. In a minute, I will tell you why this is the case. And after the declare const instruction, you have to type the name of your variable and then the type. The integer type looks like this. You have to use capital letter at the beginning. So this is how you declare a variable x of type integer. Of course, here in this exercise, we don't know what type x and y have. They can be real numbers or integer numbers. I don't know, actually. Anyway, let's start with integer numbers. Let's check if this system of inequalities has a solution over integer numbers. By the way, we should use this instruction to pick a theory. Now I'm going to pick the theory of integer numbers. So this is what I need to do. I pick a logic over integer numbers, and this is how it looks like. This is the theory of integer numbers with some extra.
It's like library in programming language?
Yes. Yes, it's like importing a library in a programming language, like using in C#, you know this instruction using.
Yeah.
So this is similar to that. Okay, I will explain a little bit later from where this abbreviation is coming, but now let's continue. So I have two variables. Now let's encode the inequalities here. So let's pick the first one. It's a okay. First of all, how to insert a logical formula, a statement which we want to check. For this, we use the assert command instruction. Okay, so after this, I would need to describe this inequality, how to do that. Okay, let me do this first, and then I will explain what is going on. So the main operator in this inequality is greater than. So interestingly, this is what we put in the first place, and we use parentheses around again. Interesting. Then the left hand side and the right hand side are written also between parentheses. So each operand must be enclosed by parentheses. Interesting, right? Okay. Then let's talk about the right hand side first. So the right hand side of this inequality is 6. So this is what I'm going to put here, 6. The left hand side is much more complicated. It's an addition of two products, basically. So how to start to encode this addition on the left hand side? Well, the main operator is addition plus, and then which has two operands again. So this is what encodes the left hand side here. I have an addition with two operands. Okay, and how to continue? So the first operand is -4 times x. -4 times x. So again, here the main operator is multiplication. Then what is multiplied with what? -4 is multiplied by x. This is how I can encode this expression. And similarly, I have 6 times y. So this is how it looks like. It's ugly, isn't it?
Don't we need more parentheses? For -4, x, 6, and 8?
Yeah, you could use additional parentheses, but I forgot to tell, if you have one single element in the parameter here, in the parameter of multiplication, you can eliminate the parentheses. So here it's not a must to use parentheses. Here it's not a must to use parentheses. You can, but
Okay.
and therefore I could also eliminate this parentheses, pair of parentheses here, right? Okay, you can make such expressions more transparent. You can always press enter. Actually, this is what I'm doing typically. So I try to make more transparent what belongs where. And maybe it's easier to see that here we have a relational operator which has two operands, this one and that one. The first operand is an addition of two expressions, this one and that one. You can also use such indentation if you want. Okay, so as you can see, this format is drastically different from the formats you got used to. It's completely different from syntax in programming languages, for example. It's completely different. But I was lying a little bit, because there are certain programming languages which use a very similar format, actually almost the same format, with those lots of parentheses, with this strange expression, with this kind of strange expression where the operator is always in front. Actually, we call this format a prefix format, which means that the operator or the instruction always comes first. This is why we call it a prefix format. Okay, so let me show you a programming language, a very famous and important programming language called the Lisp programming language. Okay, in a minute. I hope my computer won't explode. Okay, so this is a programming language which looks like, where the source code looks like, okay, here are some examples. For example, is it familiar? This is how you can calculate the sum of any number of operands here. So it looks completely the same. Or here you can see how you can declare a list of 3 elements, basically. The first 2 elements are simple numbers, but the third element is another list. This is a list inside a list.
Excuse me, I want to ask about the operators.
Yeah.
Yeah, in the example plus 1, 2, 3, 4, does it mean that it's 1 plus 2 plus 3 plus 4?
Yes.
So just one operator can replace using 3?
Yeah, in this case, yes, exactly.
Okay.
This is actually a very nice advantage of this prefix format. You cannot do this with in C#, for example. In C#, we don't use a prefix format, we use an infix format. So the operator is always in the middle. Yeah, good question. So this prefix format has its advantages. Okay, and actually not only Lisp, but other programming languages also use a similar format. Here you can see, for example, the Scheme programming language, or oh, it's interesting. There's a programming language called Clojure, which is a Lisp type language which can be compiled to the .NET framework. Actually, this is a module inside the .NET framework, or to Python. Interesting. Okay, guys, let me continue. Let's see what's happening here. By the way, do you have any other question regarding this format so far? Okay, you don't. Okay, then let's continue. We have another such inequality. It's easy to encode, so it's greater than 3. So this is what I'm going to type first. Then on the left hand side we have we have a subtraction, not an addition. The first operand of this subtraction is 2 times x, and the second is 3 times y. Okay, we are ready. We encoded this problem, so now let's solve it, which means we want to check if those two statements, two assertions, are satisfiable. I already told you how to check this. We have this checksum instruction, so this is what we have to use here. Of course, inside we have to put them inside, put it inside a pair of parentheses. Okay, then you have to click on this play button here, and let's see what's happening. Okay, and this is the result. So the SMT solver, the Z-thread SMT solver, figured out that there is no solution for this system of inequalities. It's unsatisfiable, and that's it. This was the demo here. This was the point. You don't have to calculate anything. Just you can just encode the problem in SMT-LIB. You can push this button, and the result will be provided by the SMT solver. Of course, you can also play with this example. So you can just change it, change some parts. So let's see what happens if I use less than operator here. Is the problem still unsatisfiable? No, it's not anymore. So there must be a solution already. Okay, so how can we investigate what the solution is? For this, we can use this instruction at the bottom, get model. So as it is written here, if the problem is satisfiable, you can use this instruction to get the solution, the interpretation, or in other words, the model which provides the solution. Okay, let me just try this, get model. It takes some time. Oh, jeez. I think we ran out of time. So there must be a timeout, and the solver was not able to solve it during that time frame. Interesting, because I wouldn't think that this is a difficult problem actually. What? Or there is some problem on the server side. Let me just refresh the page. Okay, of course, this is only a online interface for the solver. So the solver itself is more robust. It can solve huge problems. This is just a sandbox, a playground, what we can use. It's running out of time. Interesting. Okay, I cannot show this to you. Anyway, do you have any question? Because I would continue with the other demo.
No, I do.
No, you don't. Okay. By the way, we can, if this web page is dead, then we can try another SMT solver if we want, because I can really suggest this other solver to you. This is developed by several universities in the US, and it also has an online interface, as far as I can remember, CVC4 online interface. Okay. Here it is. Great. And since SMT-LIB is a standard format, I can just copy paste the content here and see what's going to happen. Oh. What? Okay. Interesting. Okay, so there can be some differences between solvers. CVC4 accepts only this form of negative numbers anyway, and this instruction cannot be executed because this option is off. And can I switch it on somehow?
But why here it says satisfiable?
It was satisfiable. I mean, the original problem was this with greater than the operator greater than. With it's unsatisfiable, but I changed this to less than because I wanted to check what happens if I play a little bit with the problem. Okay, I have no clue how I can switch this option on. Maybe I cannot. This is really bad. Okay, guys, I cannot show this to you. Maybe this third SMT server has an online interface as well. Let's see. Of course, the best would be to install those SMT solvers on my computer. Actually, I have them on my computer, but on my Linux how to say, operating system, and now I'm on Windows, so this is why I cannot execute those solvers on my computer. Actually, those SMT solvers are open source and free of charge. No, there is no online interface for the Yikes SMT solver. Okay, anyway, let's continue. Yeah, let me talk a bit about this logic here. You were asking about if this is similar to importing a programming library or what. It's similar, but don't forget that we are learning about logics, so it's actually about choosing a logic for the problem we want to solve. Just a minute. So in the SMT-LIB, you can pick lots of logics. Each of them has those very ugly names. Those are abbreviations actually, and I picked this QFLIA, which comes from different building blocks. IA stands for integer arithmetic, right? So I'm trying to solve the problem over integers. Then L stands for linear. Linear arithmetic is easier to solve than general arithmetic. Linear means that, it's written here, if you want to multiply or divide something, you can only do this with a constant. And actually, if you look at the problem, here I multiply x and y only with constants. So this can be encoded in linear arithmetic. And QF. So QF was in front of the name of the logic here. QF stands for quantifier free. You know, we haven't learned about quantifiers yet. Next week, we will learn about quantifiers. We'll learn about this quantifier and then quantifier. You already know them, but we don't use them in our formulas. Quantifier means basically that we use propositional logic only, without quantifiers, and it's easier to solve something in quantifier-free logic. Okay, so this is why I use this logic.
I think I know why Z3 doesn't work.
Okay, why?
Because the result should be a real number. Maybe because of it, and we're using integer logic.
Okay, we can give it a try, because of course we can also pick a similar logic, this one here, quantifier-free linear logic for real numbers, QFLRA. So it's easy to. You already tried this?
No, it's only an idea.
Okay, so let's try to solve this over real numbers then. I'm really curious what will happen. Something must be wrong on the server side.
Yeah.
No, does not work.
Oh, we tried.
It's a pity. Actually, I tried this before my lecture started, and it worked.
Oh.
Just a minute. I'm trying to check out if there are other Z-thread online interface. Okay. Maybe we can use this one. Actually, this is an online interface run by a French domain. Okay, interesting. Let's see if this works. What? Okay, maybe it seems this version of Z3 does not support real numbers, so let's switch back to integers. Yeah, worked. Okay, so it seems it does have a solution over integer numbers. If you set y to 0 and x to -2, then those inequalities hold all together. So this is a satisfiable problem, and this is one of the solutions. Okay, actually this is the solution I found before I started this lecture, so it is supposed to be a good solution, but you can check this out. Okay, I love French people. Okay, guys, let's continue with a last demo for today. So I will solve a logic puzzle with Z3, and actually in the lecture notes there is a video with one of those puzzles. So here you can find a puzzle which is called a tiling puzzle. The question is if you can how to say,
Fit?
if you can fit, thank you, if you can fit those given tiles of given sizes over this area of a given size. And this is what is encoded here in this video by me. Not the entire problem, but a part of this problem. And please watch this video after we finish here, and this will give you an idea. Now I intentionally choose another puzzle for this demo, and this is the 8 queens problem. This is a Czech problem, chess problem. Have you ever heard about this problem before?
No.
No. Actually, in the 4th semester, you will have a subject called Introduction to Artificial Intelligence or something like that. And in that subject, you will solve such problems. I mean, you will write C# programs which can automatically solve such problems, such logic puzzles. I really love that subject actually. Now we are not going to write a program. We will only specify the problem itself and put it here and push that execute button, and the underlying SMT solver will hopefully solve this problem for us. Okay, so what is this 8 queens problem? It's easy. You have a chess board, you know, it's 8 times 8, and the question is if you can place 8 queens such that they don't attack each other. So for example, this is a solution for this problem. If you check it out, none of the queens attack another one, not even horizontally or vertically, or you know, in diagonally. Anyway, this is not an easy problem if you start with an empty chessboard. How should I place my queens? So now we will solve a minimized version of this problem with 4x4 chessboard. So we are going to place 4 queens on this board, and we will see what the SMT solver tells us. Is the problem unsatisfiable or satisfiable, and there is a solution. Actually, there is a solution. Here you can see one of the solutions. So the problem must be satisfiable. Anyway, so let's encode this problem in Z3. So the logic can stay the same because we will use only integer numbers and variables. And how to do that? Okay, let's see. Okay, here I give some hints. So basically,
you have to declare 4 variables.
Yeah, we will declare 4 variables. Exactly. X0, x1, x2, x3. Okay, so let's do this. So x0, x1, x2, x3, all are integer variables. So here the idea is that in each row you can have only one queen. You cannot have two queens in one row because then they would attack each other. And basically what we store in those variables is this one, in which column the given queen is in. So we store the index of the column in those variables. So x0 stands for the very first column. This is the zeros column. So here the queen is in the second column. We use zero-based indexing. So this is the zeros column, first column, second column, third column. So basically the very first queen is in the first column. Let me just put here the solution. Okay, so you can put comments in the SMT-LIB file. It's interesting that comments start with semicolon. It's strange, but this is the case. So one of the solutions looks like that x0 is set to 1. It's in the first column. Okay. Then x1 is what? So we are now in the first row here. So in which column this queen is? Can you tell me?
3.
3, exactly. 3, 0, 1, 2, 3. So it's in the third column. Okay. Let's continue with the next queen. x2 must be equal
0.
to 0. And finally, x3 must be equal to
2.
2. Thanks, Danny. So this is one of the solutions. But let's see if the solver can find this solution by itself or it will find another solution. Okay, so now let's continue with the asserts. So we have to encode certain constraints over x0, x1, x2, x3. So the very first constraint is this one. Those variables should be inside this interval between 0 and 3. Okay, so first of all, x0 must be greater than or equal than 0, and also, oh no, also it should be less than or equal than 3, like this. Okay, you can do this for all your variables. It requires a lot of copy pastes, but anyway. Okay, so far do you understand what I'm doing here?
Why there are two zeros, x0, x0, x1, x1, x2, x2, 3, but the difference is 0 and 3.
Yeah,
Because that's the
Mhm.
columns we have, 4 columns.
Because it's the possible range of.
Not where is it exactly right now.
Yeah.
Okay.
So this is the possible range for variables. Each variable must be between 0 and 3, like this. And this is what you can specify by using two inequalities, right? Actually, we could also use a connective here, an AND operation if you want. This is something I also wanted to show you. So you can connect those two inequalities by using this AND operator. Just like in C#, but now you have to, instead of double AND, in SMT you have to use this keyword AND. Maybe it's easier to understand like this, right? or maybe not.
Yes.
Okay, but actually this and that are identical. Okay, let's continue because we are running out of time. Okay, so what else we have to do? Of course, we also have to ensure that two queens cannot be in the same column, right? So basically, two x's cannot have the same value. Do you understand that? So two queens cannot be in the same column. This is the statement for this restriction. Okay?
Yeah, it's clear.
It's clear. Okay. Then let me assert this kind of statement. So if you take two queens like x0 and x1, they cannot be the same. So the zeros, the zero queen and the first queen cannot be in the same column. This is what it means. That's it. You have to do this for all the pairs of the queens. Okay, here I made some mistake. I mentioned to you that if you want to check if two variables are not equal, you should use this distinct keyword. This stands for the corresponding version of C# in C#. So this is for non-equality. Actually, it's nice. It's easy to read. Okay, so you have to do this for all the pairs of your queens, like those guys, and then those guys, and finally those guys. So basically you need 6 such assertions to cover all the possible pairs of queens. Okay. Okay, so we already covered the horizontal attacks and the vertical attacks, but we have not covered the diagonal attacks. But you know what? Let's execute this if we get a solution. Yes, we do. Actually, it's a good solution. No, it's not. It's not. It's not easy to decode. So it says that x0 must be 0, x1 should be 1, x2 should be 2, and so on. Can you see that this is not a good solution?
Yeah, because they're placed on a one diagonal line.
Exactly, that's it. They are placed in one diagonal, exactly. So it's not a good solution. Okay, so therefore we really need this last kind of condition. I don't want to explain this, just think about it, and you can also check it, I think, in the Wikipedia page. I'm not sure. Maybe not. Oh, this is a very huge Wikipedia page, actually. You can find a Pascal program, for example, which can solve this problem. It's quite long. Anyway, let's formalize this statement. So it's a non-equality which compares two subtractions in absolute values. So let's start with the first absolute value here. Basically, again, I need to check if two expressions are different, are not non-equal. The first expression is an absolute value. By the way, there is an absolute value function in the SMT-LIB. And what is the expression? It's a subtraction of xi and xj. So it's a subtraction of, for example, x0 and xy. Okay, so this is the left-hand side for a given pair of queens. Now I'm talking about the 0th queen and the first queen. The right-hand side is an absolute value of...
Isn't should be like x0 and x3?
Yeah, I mean, we have to insert this kind of assertion for all the pairs, so 6 times. There will be one for x0 and x3 as well.
Okay.
In a minute, we will do that. So the right hand side is about subtracting the indices of x's here. So the index of the first x is 0 now. The index of the second x is 1 here. Okay, so this is the assertion which checks if the zeros and first queen are not in one diagonal. Actually, we can try this. Let's see if we get another solution. You see, now we get another solution. x0 is 0, x1 equals to 2. So they are not in the same diagonal. But this does not hold for the rest. For example, x1 and x2 are in one diagonal. So this is bad. And also, x0 and x3 in one diagonal as well. So you were really right. We have to cover that pair of queens as well. By the way, here, if you look at this expression, this only contains concrete numbers. So basically, here you can calculate the value of this expression. Here it's 1, right? So let me just rather use 1. Okay, so let's do this for all the pairs of queens. Actually, this number is the distance of the 2 rows where the queens are locating. Okay, so let's do this for x1 and x2, where the distance of rows is 1, x1 and x3, where the distance of rows is 2, and finally, let's do this for x2 and x3, where the distance of rows is 1. So this should cover all the cases. So let's see what solution we get. Okay. Oh, okay. Okay, this is a good solution. Actually, if you check out the solution we put there, it's the same. It's completely the same. x0 is 1, like here. x1 is 3, like here. Yeah, it's the same. Okay, so it worked. It worked. We just specified the problem. It was not easy, though, but actually we just specified the problem, called the checksum instruction, and the SMT solver was able to solve the problem automatically. It's really different from programming. So if you want to solve the same problem in Pascal, or you will solve this problem in C#, you will see that it can be more complicated like that. And you are the one who have to implement an algorithm for that. Here you don't have to implement an algorithm, you only have to specify the problem. This is the bright side of SMT. Do you have any question, by the way? Are you still with me?
Yes.
Yes.
Yes, but like as a first time, it will need more exercise on this. Like,
Okay.
I will try to search for more.
I know. Yeah, you are right. Okay, you can find more examples and exercises in the lecture notes with videos. This is why I recorded also videos. So please look them up, and I will show you some other source in a minute. Actually, let me show this to you. So SMT solvers are massively used in solving industrial scale problems. You can imagine that, for example, Z-thread has a C# interface. Yes, it has. So you could also use Z-thread in your C# programs. Not like this, but you could import the corresponding library, and you could call methods inside your program. And you can do this with the other SMT solvers as well. And not only in C#, but in other programming languages. For example, currently I'm using this Python library in my programs. It's called PySMT. Actually, it's very easy to use. And if you use this library, you can execute not only Z-thread, but all the SMT-LIBs which are supported. Where is it? Okay, so it seems that currently PySMT supports 7 SMT solvers. But this is not what I want to show you. You can find tutorials here. And let me show you this hello world puzzle for you, because this is an easy one to start with. So if you are interested, you could also try yourself to encode this puzzle as an SMT-LIB file. This puzzle solves this equality, actually, where all the letters are variables. We have a variable H, another variable E, another variable L. Each of those variables of range 1 to 10. And this is the problem. If you add the variables in hello and also you add the variables in word, they both should be equal to 25. So the question is there a solution for that? And if it is, what a solution can be? Actually, this problem is implemented in Python here, which can give you some ideas how you can do the same inside a program. But first, try to encode the problem in SMT-LIB and use an online interface like this one. Okay, one more thing before I say goodbye. You might wonder if there is another solution. This is the only solution for this problem, or there is another one. Well, I will try to investigate this now. It's not that difficult. You know what? I will prohibit this setting of x0. So what I'm going to do, I put an additional assertion at the end. This is kind of a cheat what I'm doing. I prohibit x0 to be equal to 1 because this was part of this solution. So let's see if the solver is able to find another solution. Okay, it was able to find another solution where x0 is 2, x1 is 0. Okay, so please check this out, if this is a real solution or it's not. And maybe there are other solutions as well. I have no clue. There must be other solutions as well, actually. Okay, guys, I think this is it. Okay, anything else you want to ask? Oleg does not want to ask anything, yeah?
No, I don't. I only want to say that this solution is also the right one.
Yeah, looks good. Okay, thank you. Thank you that you checked. Okay, guys, so please, again, please read the module in the lecture notes, and tomorrow we will meet again. And please be prepared for the test tomorrow. If you have any question, you can always send me messages in the text channel here, and I will try to answer. Okay, thank you. So bye-bye.
Bye.
Bye.